Hey, what's up, guys?
Hey, what's that?
What's going on? Wait.
What?
Oh my God.
That's what I think it is.
Oh, what?
Oh.
Particle Man. Woo! Woo!
Oh, Sydney! Look at you! Look at Sydney go! Oh my gosh, she's hurt!
Okay.
You need some Tylenol!
Tylenol? No, that's no way. Ibuprofen is the way to go.
No, Tylenol!
Don't you know how this stuff works? Like, let me tell you. All right, let's take a step back and talk about the old synthesis of ibuprofen, how they first discovered it. So, they started here with isobutylbenzene. They found that this is the molecule that is most similar to ibuprofen right here. And what's really nice about this is that it's a natural product found in Vaccinium virgatum, which is a blueberry bush commonly found in southeast USA. And yeah, what they need to do is they need to add this methyl and this carboxylic acid to the 4 position of the starting material of the isobutylbenzene. But we can see that it's kind of difficult in this case. So it's called the Boots synthesis because it was discovered by the Boots Company in 1961. And we're not going to go through the whole thing, but I want to draw your attention to all of these catalysts that are not integrated into the final product. This leads to a very poor atom economy. 40% means that over half of the molecules that go into the reaction don't end up in the final product. So it means like a lot of waste. Also, in this first step of the Friedel-Crafts reaction, this catalyst, AlCl3, doesn't even get reused because in the process, it turns into this hydrated form that has to be put into the waste. So it worked for a few years, but it was very lengthy and the Boots Company wanted to move on from this just to find a new, greener, more efficient way. So we're gonna go talk about the modern synthesis in just a few seconds.
So as Victor said, the old way of producing ibuprofen just wasn't going to cut it anymore. There was too much waste, it was inefficient, just overall not great. So we are looking at a greener approach to making ibuprofen. Greener alternatives to reactions have been pretty popular and well researched recently. Things like the Suzuki reaction have been made to be greener, which we actually just did in lab last week. And this is the new synthesis, which only has 3 steps, so 3 catalysts. And the really cool part about this reaction is that it uses hydrofluoric acid, which actually regenerates throughout the reaction. So yeah, this produces very little waste, it's very efficient, and overall greener. So, you know, that's really cool and all, but how does it all work? So ibuprofen inhibits the production of prostaglandins, which cause inflammation and pain and fever, not great things. And prostaglandins are a group of physiologically active lipids. Now, ibuprofen decreases the activity of the enzyme COX, which produces these prostaglandins, and therefore, reduces inflammation, pain, and fever. Now, the really cool part about ibuprofen is that it is sold as a racemic mixture. So your little bottle that you buy, take, it's a racemic mixture of the R and S isomers. So there's a stereocenter at the alpha carbon to the carbonyl, and the S isomer is the only biologically active isomer. So then why is it sold as a racemic mixture? That's because the R isomer is converted into the S isomer in vivo. So that means when you take it, the isomer converts and the S isomer is completely unaffected. So it just helps all around.
Okay, so we didn't go too deep into this whole reaction mechanism, but because most of it is outside the scope of this class, but there are some reactions that we learned that can take us from one to the other. For example, like this step is usually done at high pressure, but it can be done using a Grignard reagent under different reaction conditions. However, this is not really favorable at industry yet because they haven't done this with a good enough yield.
So let's see what they have to say about acetaminophen.
Thanks,
Becca.
but I really think Sydney should have Tylenol. So let me tell you a little bit about the synthesis of the main ingredient in Tylenol, acetaminophen. So this is our overall reaction to form acetaminophen. So we start with 4-aminophenol plus an acid anhydride in basic conditions with water, and that makes acetaminophen and acetic acid. And so if we come over here, this is the mechanism, and as you'll see, it's just carboxylic acid derivative chemistry. And so we start with the anhydride in the 4-aminophenol, and we do a nucleophilic attack on the carbonyl group, and then we want to push up these electrons from the double bond onto the oxygen so that we don't have a pentavalent carbon. And so then this is what we make, and we do a little proton hop here, and then we come over here, and now we have the hydrogen on the oxygen, and we have a positive charge on the oxygen. And so now the the electrons on the oxygen are just going to come back down and reform that double bond, and then this is a good leaving group, so it leaves, and we are left with the products acetaminophen and acetic acid. And so this reaction happens thanks to our order of reactivity. And so this is exactly what we learned in class, where we have the chloride is more reactive than the anhydrides and the esters and the amides and the nitriles. And that's just because of the electronegativity of the derivative. And so
the more reactive group is replaced by the less reactive group
because it's going to form a more stable compound. And so because the anhydride is in this more reactive group and the amide is in this reactive group, this reaction can actually happen without catalysis. And so we can see that the anhydride has this nice resonance structure right here where we can polarize the carbonyl because the oxygen is more electronegative than the carbon. And so as you'll see, it leaves a positive charge on the carbon, leaving it susceptible to nucleophilic attack. And if we come over here, side note, why don't we do this in acid? As you'll see from before, we do it in basic conditions. Well, that's because we would simply protonate the amine group on the 4-aminophenol because amines are bases. And so when that happens, we're left with a positive charge on the amine group, which makes it a really bad nucleophile because nucleophiles are seeking a nucleus, and they usually have excess electrons to share. But instead, we have a deficit of electrons here. And so now, I'm going to hand it off to Sydney to talk about what this molecule does in our body.
Thanks, Katie. Let's take a look at how Tylenol works in the body. Acetaminophen, the main ingredient of Tylenol, does not have anti-inflammatory effects like ibuprofen does and like how the rest of the non-steroidal anti-inflammatory drugs do. What they do have in common is that they both block prostaglandin, which has to do with pain, which is this molecule here. The difference is where acetaminophen is a weak inhibitor of COX, which has to do with inflammation. So all that acetaminophen can do is decrease the pain threshold by working in the brain and in the spinal cord. So Tylenol is better for things like fever and for general pain, while ibuprofen is better for pain in a certain area and for inflammation. So if you've ever heard of Tylenol working better above the neck and ibuprofen working below the neck, that's where that comes from. Quick side note, acetaminophen is easier on the stomach because of the absence of this carboxylic acid group, nowhere found in the molecule. But it can be very toxic to the liver if taken excessively, so you should always follow the dosage on your label. What happens with ibuprofen though is that it can cause a stomach ache because it does have this carboxylic acid group in it. So in this case, for a broken ankle, ibuprofen would be better. Here you go! Ow! I guess ibuprofen is right for me. Thanks, guys!
No! Wait, no!
As a disclaimer, Sydney did not really take this many pills, Please follow the recommended dosage, which can be found on the back of your drug bottle.